case. So next we'll see what is the maximum power transfer theorem. Okay, so maximum power transfer theorem is basically the extension of your Thevenin's theorem. The Thevenin's theorem, we have seen that any linear bilateral active network can be reduced to a simple network where in which we will have only one voltage source called Thevenin's voltage source and a resistance called equivalent resistance called Thevenin's resistance, right? Now maximum power transfer theorem states that maximum power is actually delivered to the load when the load resistance value is equal to the Thevenin's resistance. Okay, so basically it's a continuation of your Thevenin's theorem where we are going to find out the R Thevenin value, V Thevenin value, and we are going to get your Thevenin's equivalent circuit, and then RL value you are going to replace it with your R Thevenin, and with R Thevenin power transferred to the load will be the maximum. Okay, so let's see how does we'll just do one problem based on that. So maximum power transfer theorem is nothing but your load resistance you are going to replace with a Thevenin's resistance, right? In that condition, maximum power will be delivered to the load. So I'll just refresh the Thevenin's theorem itself here. Any complex network can be reduced to a simple network which has got a voltage source in series with the resistance. The voltage source is called your V Thevenin and the equivalent resistance is called Thevenin's resistance, and we have RL. So in a maximum power transfer theorem, if RL is equal to R Thevenin, the maximum power is delivered to the load. Okay, so let's see how does or the maximum power, what is the quantity of the maximum power which is delivered to the load. So from this circuit I can say, let's say that the load current is IL. Okay, so we can write down IL value here. So IL is equal to V Thevenin divided by R Thevenin plus RL. Now in maximum power transfer theorem, this RL value I am going to replace with R Thevenin. So we will get V Thevenin divided by R Thevenin plus R Thevenin. Okay, so that is V Thevenin divided by 2 R Thevenin. Now the power equation, we know that P is equal to I square R. So I can write this as IL square into R. Okay, so that is, since your R Thevenin and RL value is basically in series, I can write this as R Thevenin plus R Thevenin. So IL, I am substituting this value here. So that is V Thevenin divided by 2 R Thevenin the whole square into R Thevenin plus 2 R Thevenin, I will write it as 2 R Thevenin. So this is nothing but V Thevenin square by 4 R Thevenin square into 2 R Thevenin. So this gets cancelled, 2 get cancelled. So you'll get this as this we have to do it for RL alone, right? So power across a load we are seeing. So PL equal to IL square into R Thevenin. So this will be only R Thevenin. So you can write PL equal to IL square into RL. IL value is V Thevenin by 2 R Thevenin whole square into RL. RL is nothing but R Thevenin. So it is V Thevenin square divided by 4 R Thevenin square into R Thevenin. You can write this as V Thevenin square divided by 4 R Thevenin. So this is the equation for maximum power which is to be delivered to the load. Okay, now let's do one problem on maximum power transfer theorem. So we have to find out the maximum power by using power transfer theorem. Okay, so let's take one example. So some 10 volts, 2 ohms, okay. So for maximum power transfer theorem also, we have to initially get the equivalent, Thevenin's equivalent circuit where your value is V Thevenin and R Thevenin has to be calculated. So this value, RL value, you have to substitute it as R Thevenin and find what is the maximum power. Okay. So in this condition, first we are going to find what is your V Thevenin. So V Thevenin, I've told you already in the last session that to find V Thevenin, you have to open circuit the load, short circuit the voltage source, and open circuit the current source if any. Okay. So here we don't have any current source, so we can, sorry, that is for R Thevenin. So for V Thevenin, we have to open circuit the load and find the open circuit the load and find the open circuit voltage. That is your V Thevenin. Okay. So I'm writing this as 10 volts to this is your V Thevenin value. Okay. So 10 volts, you have 2 ohm, 2 ohm, 2, 2 ohm, 2 ohm, and load circuit is open circuited. So from here again you can say that V Thevenin is equal to voltage across 2 ohm plus voltage across 2 ohm. Okay. So here we know that since it is open circuit, the current is equal to 0. So V Thevenin should be equal to voltage across this 2 ohm. Okay. Now to find out the current through this, we can directly use the loop analysis. I'm assuming that this is I1 and this is your I2. This loop we are not considering because it's open circuit and current is actually 0. So directly writing using inspection method, we can write 4 R12 is minus 2, 21 is minus 2, 6, first loop alone we have got a voltage source, second loop it is 0. So for here you can find what is your I1 and I2 value. So once you get the value, the I2 value, you can substitute it in the equation and find what is your V Thevenin. Okay. Now to find out R Thevenin value, that is similar to your Thevenin's theorem itself. And for R Thevenin, So to find out R Thevenin, we have to short circuit the voltage source, open circuit the load, and open circuit the current source if there is any. Okay, so I'm going to short circuit the voltage source here. 2 ohm, 2 ohm, 2 ohm. So here you have 2 and 2 are in parallel. So 2 parallel to 2. The whole combination is in series with the 2. So you can write plus 2. Then find what is the, and this combination is in parallel with this 2. So that is 2 plus 2. That is your R Thevenin value. Okay. Now you can substitute the value of R Thevenin, that is 4 by 4 is 1. 1 plus 2 is 3. 3 into 2 by 5 plus 2. 6 by 5 plus 2. That is 6 plus 10 by 5. That is 16 by 5 is your R Thevenin value. Okay. Now in your circuit, RL value, you are going to substitute it with the R Thevenin value and substitute what is the value, whatever we have obtained for V Thevenin, and find out what is the IL. So IL will be again V Thevenin divided by R Thevenin plus RL. Power is equal to IL square into R Thevenin. The next topic that we have is a superposition theorem. So superposition theorem states that in any linear bilateral network having a number of sources, right, with more number of elements also, the current in any element is equal to the algebraic sum of the current due to the individual sources acting alone. Okay, so any network we may have a number of sources and we may have a number of elements, and the current in any one element should be equal to the algebraic sum of the current due to the individual sources acting alone. Okay, so it's like if you have, let's say you have got a voltage source V1 with 4 or 5 resistance, let us draw simply as R1, R2, R3, and I'm drawing another resistance R4 in series with a voltage source again, that is V2. Okay. And maybe one more voltage source, I can draw it as V3. Okay, now if I want to find out the current in R2, that is I R2, if you want to find it, we have to find out what is the current in R2, and the current through this R2 is going to be the algebraic sum of the current in R2 due to the individual sources. Let's say I keep only V1. I'll keep only V1 and find what is the current through your resistance R2. And second step, we are going to keep only V2 and find the current through R2, and V3 and find the current R2. So whenever we are going to do this, first we have to keep only one source and short circuit the other sources if it is a voltage source. Now if there is a additional source is actually a current source, then we have to open circuit. So voltage source has to be short circuited, current source has to be open circuited. Okay. So at a time we are only considering only one source. So V1 alone when I am considering, V2 and V3 I am going to short circuit and find what is the current through R2 due to V1. Okay. Next we will take V2 and find what is the current through your R2. So let's say so I am writing this I current through R2 due to V1, I can say I dash, and current through R2 due to V2, I will mark this as I double dash, and current through R2 due to V3, I can mark this as I triple dash. Okay. Now let's say that I'm going to keep all the three sources and finding the current through this. Okay, that is actually the total current which is flowing through your R2. That will be equal to the individual current because of the individual sources. So that is here the total current I total should be equal to I dash plus I double dash plus I triple dash. This is called a superposition theorem. So I'll tell once again, for a superposition theorem, we'll have more than one source. So if I'm keeping all the sources, you may get 1 volt, 1 current, right? And individual sources I'm keeping it and finding what is the individual current. Algebraic sum of these current will give you the total current through your resistance R2. Okay, so that is called your superposition theorem. Let's do one small problem. I'll take a voltage source of 50 volts which is connected to a resistance 10 ohm and another resistance 3 ohm and 5 ohm and 25 volts. Okay. I have taken a circuit with two sources of 50 volts and 25 volts. Okay. Now I have to find the current through 10 ohm, and 5 ohm by using superposition theorem. So for using superposition theorem is nothing but I am going to keep one source alone and find the current through 10 ohm and 5 ohm, and then second one I am going to keep 25 volts alone and find the current through this. And for proving the superposition theorem, we have to keep both 50 volts and 25 volts and find the current through the elements. So the algebraic sum of the current through the element due to the individual sources should be equal to the total current which is flowing through the element. So first case we'll see when 50 volts alone acts. So when I'm considering the 50 volts alone, 25 volts I have to short circuit it. If there is a current source, you have to open circuit, and if the voltage source, we have to short circuit it. So I'll take this as 50 volts, you have 10 ohm, 5 ohm and 3 ohm, and find what is the current through 10 ohm and 5 ohm, or we can simply find the loop currents I1 and I2. Okay, so I'm just writing the equation by using inspection method. You can say 10 plus 3 is 13, minus 3 and 8. I1, I2 equal to V1 value is 50 volts, and in loop 2 we have no voltage source, so I am writing this as 0. Now you can, once you solve this equation, you can find that I1 will be equal to 4.21 and I2 you will get this as 1.578 amperes. Okay. Now, so this is nothing but the current through the first loop and second loop due to the voltage 50 volts alone acts. Okay. Now the second case, when 25 volts alone acts. So 50 volts has to be short circuited, and you will have 10 ohm here, 5 ohm. I'm keeping 5 volts as such, and 3 ohm. We'll take this as I1 and I2. This is 25 volts. I'm going to find out I1 and I2 due to the voltage source 25 volts. So this is again 13. By inspection method we can write the equation directly. Minus 3 and 8. I1 and I2 equal to, now in the first loop there is no voltage source, I can write the 0, and second loop it is minus 25 volts. So in this condition, if you find out the value for I1 and I2, I1 value you will get this as 0.789 amps, and I2 we will get this as minus 3.42 amperes. Okay. Now the third condition, I'll just find out what is the current through 10 ohm alone. So third case is when 50 volts and 25 volts alone acts. Okay. So I'll just take this as, let's take current through 10 ohm because of the voltage source 50 volts, as I'll write this as I10 ohm dash, that is nothing but I1. Okay, I1 is 4.21 ampere, and due to the 25 volts the current through 10 ohm is I1, that is minus 0.789. So I'll write I10 ohm is equal to minus 0.789 amperes. Now when we consider 50 volts and 25 volts together, we should be getting the answer for, that is a current through your 10 ohm, as the algebraic sum of this first case and the second case. Okay. So directly I can write it from this itself. The equation is 13 minus 3 minus 3, 8 I1 I2 equal to 50 and 25 minus 25. Okay, if you find this, you will get the value as I10 ohm. If you equate it, it's nothing but I1 or I10 ohm, you will get it as 3.42 amperes. Okay. Now if you see here the first case, I10, current through the 10 ohm due to 50 volts is 4.21, and due to the 25 volts it is minus 0.789. Okay. So from the theorem you can say that I1 dash plus I1 double dash is equal to 4.21 plus minus 0.789, that will be 3.42 amperes. So if you see this, it's actually I1, that is with 50 and 25 volts together. When we did the calculation, it was 3.48 amps, and otherwise it is, again if you add up the algebraic sum in both the cases, that is when you are considering the individual sources alone, right? Like when you're considering one source at a time, and if you're going to add up the algebraic sum of the currents, you will get the same value as your 3.48 amps.